The next thing to talk about in any given calculus class would be the exponential function. And to give away the ending, the derivative of e to the x is e to the x, and that makes it a beloved function in mathematics. In fact, sometimes this equation is taken to be the definition of e to the x. And if we take that as a definition, then no proof of this law is necessary. We're just saying that e to the x is whatever function satisfies this equality. So by definition, this equation is true. Now, however, many viewers will be familiar with e as being some number that they saw in high school defined perhaps by some limit formula. And if that's your definition of e, then a proof is demanded here. Now, a direct proof I find really nauseating. I've seen a couple of them, and I did not feel like I was any better for having seen them. So I will not do a direct proof, but I do know of an indirect proof that goes by way of a few facts that you need to know anyway. A typical calculus class will introduce you to the inverse law anyway, and it will show you the derivative of the logarithm, the proof of which is not too hard, and if you put those together, you can get a proof that the derivative of e to the x is e to the x. So in fact, that's the way that I'm going to do this. But keep in mind, you do just need to know this. You probably shouldn't be proving it to yourself every time. You should just know this by memory. It's a pretty important and remarkable fact as it is. So just know that. Always have that at your fingertips. Anyway, let's talk about the inverse law. So suppose that you have a function that is invertible, and I assume that you know what invertible means from high school, and therefore the inverse function exists. But invertible, well, okay, I'll just say it. It means this equation, that there exists an inverse function such that f of f inverse is equal to x. And that's the definition of an inverse function. Basically, doing the function and then undoing it does nothing. So whatever you put in is exactly what you get out. Anyway, now suppose that we are wondering what is the derivative of the inverse function. Well, it makes sense to just look at this equation and realize that we could take the derivative of it and work our way toward the answer. If we take the derivative of both sides, then especially the derivative of x is obviously equal to 1, and the derivative of this part is given by the chain rule, so that I take the derivative of the outer function, plug in the original inner function, and multiply by the derivative of the inner function. Hey, this last part is exactly what we're asking about. It's what we're trying to find. So we solve for it. And we solve for it just by dividing this junk to the other side underneath 1. And there we have it, the inverse law for derivatives. Now we can actually solve a particular problem using this law. So let's take f of x equals sine x, and let's try to find the derivative of its inverse, which is sometimes called arcsine or sine inverse. So what is this derivative? Well, putting into the formula, we get that it's 1 over the derivative of f, which is obviously sine, composed with, plug in, the f inverse function, which is arcsine. Now, this is a little bit unpleasant because arcsine is unpleasant, and we'd like to eliminate it if we possibly can, and we can through the following. Now this is somewhat more advanced trigonometry, so I would forgive you if you didn't recall it perfectly, and I'll go ahead and explain it, therefore. So if we're plugging something into arcsine, then that must mean that what we're plugging in is a length. Arcsine is only defined between -1 and 1, so it only accepts arguments that basically represent the edge length of the opposite side of the triangle, right? I mean, because we're talking about sine, then we're talking about the opposite, and since, with regular sine, you plug in an angle and get out a side length, well, with arcsine, you plug in a side length and get out an angle. So arcsine of x is an angle corresponding to a length of the opposite edge being equal to x. So I draw my arbitrary triangle, I draw my unit circle and then point to where I have a y coordinate equal to x. That's a little confusing, but you know, because we're calling it arcsine x, I'm just going to kind of stick with it. We know that the opposite edge of this triangle has length x, and this inside here, I'm going to call theta. Oops, will it? Okay, so the angle, the reference angle is theta. And theta is equal to arcsine, right? This is just how arcsine is defined, is you give me the edge of this triangle and arcsine reports back with the value of theta. So we are taking this angle, the angle theta in this, the reference angle, and we're plugging it into cosine. Well, cosine just tells you the length of the adjacent. So this is cos theta. It's not going to let me do it with parentheses. Anyway, okay, there, cos theta. So so this edge is cos theta. So one other thing to remark is that because this is the unit circle, we know that the hypotenuse length is 1. And putting all these facts together, we can state the Pythagorean identity, that this squared plus x squared is equal to 1 squared, which is just equal to 1. And by taking that and solving for cos theta, which really is the same thing as cos arcsine x, right? This is cos arcsine x, so it's really the thing we're trying to simplify, is this thing right here. And if you throw all this information into the Pythagorean identity, you will get that cos theta is square root 1 minus x squared. So we replace it with exactly that, and this is in fact a much nicer statement or answer for what the derivative of arcsine is. And now we're done.